This video introduces Tafonius Junior and all the relevant parts, and is more of an anatomy lesson than anything else at this stage. In this video we'll run through the different parts of the Tafonius Junior, what they do, what they mean, and go into some more detail about some of the features of the machine. To start with, we're going to look at the machine as it stands now, with a picture of a front-on view on the screen in front of you. And we're just going to go through the main component parts. So on the left we have the oxygen flow meter shown here. This takes piped oxygen from the back of the machine and feeds it into the anesthetic circuit contained within Tafonius Junior. I should say here that this machine that you're seeing is actually a Tafonius Junior with most of the options fitted. There's also an air flow meter fitted here. There's additional arms here for maneuverability and carrying, which I'll show you when we see the side view. It has a circle system fitted, and also has a Select Tech back bar fitted here on the right hand side. The standard machine will have a cage mount vaporizer fitting, but Select Tech back bar is an optional extra. Okay, so we have the oxygen flow meter, we have the air flow meter here. Moving to the front of the machine at the top here, we have a typical manometer gauge to measure the airway pressure. Below that is the hospital oxygen gauge for incoming pressure from the hospital supply or from any e-cylinders, oxygen e-cylinders that may be fitted to the Junior. Below that is the white oxygen flush button, delivering 70 litres per minute when pressed, and that 70 litres a minute does not go through the vaporizer. Again, to the right we have the auxiliary screen shown here with information about the machine, the patient's efforts for breathing, the settings for tidal volume, etc. We'll come back to this in more detail later. And around it are several buttons and knobs which control the machine to allow features such as ventilation, CPAP, PEEP, assist mode, and even things like add a litre of oxygen at will. Below the main front console and at the back, shown here, this is the actual motor that's driving the piston, which sits inside this cylinder, which you can see slightly hidden behind the oxygen tubes. But again, we will see more of this later. And the orange and the green wires you see here are just the control wires to the motor. At the front here we have the main valve block, which has a clear perspex lid showing clearly the two valves from the inspiratory, which is on the left side, and the expiratory side, which is on the right side. This clear lid is held in place by 6 black thumb screws, and these can be removed to take the lid off, remove the valves, and do a thorough clean. Here we have the two 2-inch patient tubes which will lead down to the Y piece, which we'll see later, and to the back here we can see just a bit more of the cylinder. And I'm just going to show you. Here is one of the retaining straps or clasps for the soda lime tray, and the other one's just to this point here. Just about to see it there. There are 3 retaining clasps on Junior, 2 at the front and 1 at the back. Also on the Tafonius Junior, on this machine, you can see there are 2 areas here for some e-cylinders to be fitted. One on the right hand side here, one on the left hand side here. They can hold 1 oxygen e-cylinder here and 1 air e-cylinder here, or vice versa. You can see here on this machine I've got an option for an oxygen e-cylinder fitted here with the white tube coming down, the white hose, and oh yes, you can see it on here. There's a black hose coming down here to connect to the e-cylinder for an option for an air cylinder. On the left hand side of the machine you'll find the manual breathing circuit shown here with the 30 litre bag, spill valve, and the corrugated tube leading down, and at the moment this is held fixed in position, so it's not in circuit. If this were to be connected in circuit, if it was needed, this red cap would be removed, and we'll connect this end of this hose to one of the outlets at the bottom by removing one of the bungs, but we'll see those more clearly in another picture. Also we see here we have the inlets, the NIST inlets for the different gases, and that's where these are attached to the machine. Again here we see slightly more clearly the position for the oxygen E cylinder on the side of the machine, and we see the Y piece hanging on its bracket with its protective collar and its connected side stream sampling port just here, and the patient pressure sensor line just coming down here. We'll return to all these items in slightly more detail as we go through this video. This picture shows more clearly the connections for the hose fittings, which use NIST fittings, which is non-interchangeable screw threads. What that means is that you can't connect by mistake the oxygen hose to the air inlet and vice versa. On this machine there's no nitrous fitted, although there is an option for nitrous on any machine that you purchase. At the bottom we have the vacuum line taking air and gas away from the machine to a standard vacuum circuit. At the other end of the hoses we have, in this instance, the British BS probes that we will fit, but these probes can be replaced by any fitting peculiar to the country that it's being shipped to or being used in. Here we see the back of the machine, and at the back of the machine we have the mains power cable coming in here through this protective glands and up into the machine via these fuses here. If I can zoom in on here, you'll see that there are 4 fuses here. They are 5 amp fuses, and there are spares hidden or held within the machine. To the left of that we have the RCD or residual current device, and this is the first point where the electricity goes into the machine, and if there's any problem with earthing or a power surge, this will trip out. So it's quite important when checking the machine or turning the machine on to make sure that this trip switch is not off, and make sure the green light is on, indicating that mains power has been fed to the machine. Because the machine will work adequately on batteries for several hours, it can become unnoticed that there's no actual mains power being delivered to the machine, and then you get a nasty surprise when the machine starts beeping at you that the batteries are low. Here, this cinch strap is simply here to hold the coiled up mains wire when the machine is being moved or put away, and the cinch strap here is for coiled up oxygen and air hoses, again when the machine is being moved or put away. If we go to the lower part of the machine, look down here, as we briefly talked about just now, these are the 2 drainage bungs which can be fully removed at the end of the day to allow cleaning, flushing and drainage of any water and fluid from the machine. And as mentioned briefly just now, if the machine has a problem or the batteries are flat and you wish to ventilate, then the manual breathing tube will fit snugly over this connector here on either side once the bungs have been removed, and in that way the manual breathing circuit can be used to ventilate a patient like a standard rebreathing circle system for any horse. What's not maybe so obvious is that the soda line tray is actually this item here. In a minute we'll see this whole system opened up, and it'll become clearer what the soda line tray actually is. This is the soda line tray. This is one of the retaining clasps, and we'll just come to that in a moment. These are the hydraulic rams which make it easier for you to open and close the cylinder. And these are the leaf springs that pop into place to keep the cylinder open. One other thing we can see from the back, if we zoom up here, is we have an F-air canister here, or charcoal canister, which comes from the evacuation valve from the machine. Now with scavenging and normal use, this F-air canister is rarely used. It's there really to have 2 catch-all or security functions. If for any reason the scavenging or waste system isn't operating sufficiently to remove waste gas from the system, then the pressure that's generated will force it out through the F-air canister. the activated charcoal in here will remove the agent in use, and only clean air will be let into the room. Conversely, if the machine or the patient circuit senses a negative pressure in the patient circuit that falls below -8 centimeters of pressure, in other words it's more negative than -8, then this dump valve, or the dump valve that you can't see up in the machine that connects to this manifold, will open and allow fresh air to come in through the air, therefore being filtered, and then up into the patient circuit, so that the patient cannot see a negative pressure of greater than -8 centimeters of water. We're now going to look at some of the items that we briefly discussed in more detail. This is the RCD, or residual circuit device, or known in other fields as GFI, ground fault interference unit. The sole purpose of this is to protect the user from inappropriate earth currents, so that if any current flows from neutral or live to the earth circuit, then this trip will switch and the mains will be removed from the machine. As you can see here, there's a little green light indicating that the mains power is applied, and the button up here is depressed and the little 1 is visible just here, indicating that the switch is on. Here it says test, and if you press this little button in normal use, this should trip the switch out, which I've done here. Pressing that button, the little LED has gone out, the switch is tripped off. We now see a 0 up here, indicating that the main supply to the machine is off. And do remember that even though this is off, does not mean that the machine will not work, because it will run on batteries at this point. And the takeover is automatic. There's nothing you need to do. If the mains fails at any point during an anaesthetic, then the switchover is automatic and the machine will continue to function exactly as it was when the mains went off. Just looking at the side of the machine here, we can see the position of the F-air canister, which we briefly discussed. We can see the air connector for the E-cylinder here, and here we have another optional lecture, which is the IV pole, bolted here, fixed here, and of variable height, which we can see from the next slide. So we see here that this IV or bag holder has a clasp here which you can tighten and untighten, and then raise this part to the desired height and then tighten this again. This is an optional extra, can be added to any machine, not just a Junior, can be added to a full-blown Tafonius as well. But now we're going to have a look at the soda lime tray in the Tafonius Junior and go through its removal process. As I mentioned before, there are 3 clasps that hold the soda lime tray in place. Here's one at the front, and we saw one at the back, and we saw the 2 at the front earlier on. To undo these clasps, there's a little bracket clasp here that needs to be undone in a particular way. If you get down and look at the bottom of the machine, the bottom of this little clasp has a sprung rod or spigot here, which you have to push down away from the front of the machine to release. This shows the spigot being pushed away, and now it's in a position where the clasp can be pulled down and released. Once all 3 clasps have been released, then place your foot on the foot plate as shown here and push down. Push down until the leaf springs slip under the hydraulic rams and stop them going back, stop the soda lime tray going back up. Make sure you do this on both sides, and then you'll have the soda lime in this tray in this position. Here we are, the tray is open, the leaf springs are slipped under the hydraulic ram here and under the hydraulic ram here, and we can now pop this by giving it a little sharp tap because it's stuck to the rubber here. Tap it here, the soda lime tray will drop down and can be removed. When it's removed, it looks like this. So as you can see, what we have now, remember from the front we had the valve block and the descending corrugated tubes going down. This is the inspiratory side, this is the expiratory side. So gas is going to return from here, come in here, come up through this hole into the bottom of the soda lime tray. And the soda lime tray itself is split, so it'll go through this side of the tray first, up over the top, and then down through the soda lime on the inspiratory side, through this aperture, and then up the tube and back to the patient circuit. And what you see here, this orange seal here, is a seal between the absorber pan tray and the soda lime canister. Now this seal has no bearing or effect with regards to leaks in the patient circuit. It merely stops gas passing from this side of the circuit to this side of the circuit and prevents it going across there rather than going up and through the soda lime. So this seal marries with this seal on the bottom of the soda lime tray, and that's why this tray has to be put in only one or two ways, but this main seal on the bottom must line up with the main seal on the absorber pan, and in this way gas cannot pass from one side to the other. If this seal or this seal become damaged or worn, then you may start to see a high inspired CO2 value on your capnograph, because exhaled gas is bypassing the soda lime and going straight to the inspiratory side. That's quite rare. These seals are very good. They don't soften too much with use, and they normally prevent that happening. But just look out for breakdowns or crumbling of the orange seal here and at the other end particularly, as they may be the first places to go, and then when you may start to see an inspired CO2 problem. Once the soda lime tray has been emptied and refilled, it's put back in with this seal in line with this one, and then pull these two leaf springs together, and the hydraulic ram will pull this soda lime tray and the absorber pan up tight against the bottom of the cylinder. Then place the two, or fasten the two clasps at the back, refit the clasp at the front, and tighten those by pulling the clamps down and snapping them into place. Okay, we're just going to look at the patient circuit in a little more detail. As we talked about before, we have the valve block here with the inspiration or inspiratory side here, expiratory side here, running down to the Y piece. And I want to point out one fairly innocuous but very, very important feature of the machine, which is a little tube that runs down here and goes down and, as we'll see, connects to the Y piece at the front. This tube is the patient pressure sensing tube, and it's very important to the role of and perfect function of Tafonius. It connects to a little lure connector here, and as we see on this slide, it comes down and connects to a little lure connector here, which takes it to a little swivel head connector which senses or measures pressure in the Y piece. And this is crucial to the way Tafonius, not only in Junior, but all machines work. The way it works is that whenever an increased pressure or fall in pressure is sensed in this Y piece here by as little as 0.25 centimeters, the machine will then, in servo mode, move to negate that pressure change. In other words, if the animal breathes out and it raises the pressure here by 0.25 centimeters, this will be sensed in this sensing tube, and the piston will move up by whatever is required to return the pressure in here to zero. This servo function means that animals as small as 10 kilograms and as large as 2,000 kilograms can breathe confidently and easily on this without experiencing any resistance due to the tubes, the soda lime or the valve block. If this sensor isn't connected, then the machine will still function, as we have an auxiliary sensor which is actually coming in at the back of this valve block and will measure the pressure. But as you can probably appreciate, the pressure measured at this point isn't so good at controlling the airway pressure at the Y piece as it is directly at the Y piece. And so the machine, although will function, will behave not as well as normal, and the pressure variations will be much greater in the patient's circuit than you would expect. Before we leave this video, I'm just going to introduce the main features of the auxiliary screen system and the associated buttons. We'll cover this more fully in another video where we'll look at actually setting and using the ventilator to ventilate a dummy patient. For now though, we're just going to introduce the auxiliary screen just to get an idea of what it offers. So the main screen is shown here in the center. At the top we have the battery values for the two batteries inside the machine, and as you can see next to that in the center it says BAT. If this was a live video rather than a picture, you see that BAT would be flashing. It flashes there to alert you to the fact that it's not running on mains and that you're running on battery power. To the left, the battery's actual voltages are shown here. Battery 1 is 12.3 volts and battery 2 is 12.2, and they're both shown as OK. As these values decrease, this is constantly updated. If any of them gets to a low or critical value, it'll A show here on the screen and also be indicated by a warning error that will flash up in this area of the screen here. To the right of the battery symbol or battery name, we have the software version, which on this one is 6025, and then in brackets we have a number which in most instances will be increasing, and that's the time between the vacuum pump running. The vacuum pump is a little pump that is responsible for keeping the vacuum in the two silicon diaphragms that form part of the piston mechanism. It's important that the vacuum is maintained, and we can see here that the vacuum level is set as -14. Typically you'll see within these brackets that this value will rise until it gets to a value of 255 or greater. It'll then be reported as 255 seconds, which would be normal. At the moment I've just turned the machine on. We've had 2 seconds of vacuum since the pump ran. This will, as I say, increase and show you at all times the vacuum interval. Below that we have the sort of status area, and we have two alerts on the screen at the moment. We have the first one, oxygen supply pressure is low because there's no oxygen supply connected, and we have cylinder empty out of reserve. If we look at this area, this is the representation of the cylinder and the piston. It says 0.0 litres because the piston is right at the bottom, and rightly so. The warning error is that the cylinder is empty or out of reserve. While we're talking about this now, this ties in quite nicely with this add a litre feature or add a litre button. When the switch is up, as it is now, it's in the on position, and if we had oxygen connected and there was any slight pressure in the system, then the machine would automatically add a litre of oxygen through the vaporizer to put some more gas into the system. The way this works is that when you're ventilating a patient, and if you're getting down to the lower regions of a litre or less, then the machine will automatically add extra oxygen to stop the cylinder running out of gas. If you turn this switch or push the switch to the lower position, switch it down, then it's off and that feature is disabled. Looking at the screen now, as we just said, this is the area that's represented by the piston. To the right of that we have the actual volume of gas under the piston. Then we have a value called BV, which is the buffer volume, and this takes a little bit of explaining. The buffer volume is an independent volume which, when added to the tidal volume, which is set here, forms a total which is then accepted by the machine to be the sort of virtual bag size of the circuit. So in a normal circle system, you'd have a bag on the circle of maybe say 2 litres, and once that 2 litre bag was full, the pressure would rise, the spill valve would open and the gas would evacuate. So you'd never exceed a bag size of 2 litres because the gas would escape. In Tafonius you can decide your own bag size. So in this instance we have a buffer volume of 5 litres and a tidal volume of 5 litres. Add these two together, we get a total volume of 10 litres. And if we were to fill this system with gas now, we see the piston rise up here until it got to the midpoint, which is 10 litres. And at 10 litres it would stop moving up, because the virtual bag size is set at 10 by the combined value of the buffer volume and the tidal volume. If we set the buffer volume to 10, then the combined size would be 15, and this would rise up to the 15 litre point and stop up here and not get any bigger. What this means is that you can actually control very carefully your circuit volume, so that when an anaesthetic is started you have a big circuit volume, the patient's allowed to take big breaths, and then once they're asleep and finally controlled, you can reduce the circuit volume, which improves your time constants for changing vaporizer settings. Under here we have MWPL, which is mirrored down here by the MWPL button, and at the moment it's set to 57. That's centimetres of water, and MWPL stands for maximum working pressure limit. What this means is that if the pressure in the circuit ever reaches this value of 57, which is unusually high, would normally be expected to set around 30 to 35, then the dump valve will open and any excess gas will be allowed to escape, and if we're ventilating, the inspiratory phase will stop. So it's a safety feature, and the pressure won't be allowed to rise above the value that's set by the MWPL. Under that we have the assist value, which is currently at 60. This means that in assist mode, which isn't set yet but is controlled by this button at the top here, that in assist mode, if the patient was to inhale at a rate greater than or equal to 60 litres per minute, then assist breath would be triggered. We'll cover this more fully in the video. Underneath that we have a CPAP value of 0, and the CPAP is set by this button here, which says PEEP or CPAP, depending on which mode we're in, whether we're ventilating or spontaneous breathing. Pressing this CPAP button means that the MWPL will change to say CPAP, and we can set it with this knob. At the moment it's set to 0. Then on the right of this we have the minute volume, 25 litres. That's simply composed of the tidal volume times the respiratory rate. We have the inspiratory flow, 75 litres per minute, simply calculated from 5 litres delivered in 4 seconds. And we have the IE ratio as 1 to 2. We have 4 seconds of inspiratory time. We have a respiratory rate of 5 seconds, which is 12 seconds per breath, 4 of which are inspiratory time, so the expiratory time must be 8. So we have 4 seconds of inspiration, 8 seconds of expiration. We must have an IE ratio of 1 to 2. These values are resultant values, and these are automatically calculated and updated immediately. So changing any one of these knob values will change the values that are shown up here. At the bottom we have 4 major knobs and their associated values. We have 1 tidal volume, 2 respiratory rate, 3 IT inspiratory time, and 4 MWPL, as we've seen, maximum working pressure limit. At the moment tidal volume is set to 5. This can be set to anything between 0.1 and 20. The respiratory rate is set at 5, can be set between anything between 0.5 and 30, I believe. And inspiratory time, anything between 4 and down to 0.5. MWPL up to 80 and down to 5, I believe. Anytime any one of these values is changed, it will show a little asterisk here. We'll see this clearly on the video that describes this. A little asterisk appear, and you must push the button to commit the value. Otherwise, the value will just return to its original value before you made the change. And to sum up, and to just show what these other buttons are, we have a dump valve here. Pushing this will force the piston to descend and try and attain a pressure in the system of 5 litres per minute, but at the same time the valve is opened to the back of the machine, and this means that gas is forced out. So that's an evacuation or dump valve. The power button is here. Press once to turn it on. Press and hold for 3 seconds to start the process of closing the machine down. At the moment we don't have a simple recruitment maneuver, so this button is a blank. Up here we have the assist button that we've seen to set the assist value, the PEEP and CPAP button, and here is the run or IPP button. To change from spontaneous breathing to ventilation, simply press this button. This will illuminate and the machine will go into the IPPV mode. Press it again, the light will go out and the machine will go back to the spontaneous mode. There is no need to make any other changes to change between spontaneous mode and ventilation mode. This concludes the video describing the Tafonius Junior parts. There is another video which will show you more clearly how to use these parts of the screen, how to set them up and how they behave.